Okay, so now that we have a way to interpret the speeds of our gas particles, or the speed of the particles in the gas sample, we can now make some comparisons between different gases that are at the same temperature by comparing the root mean square values for those different gases. So if we want to make some comparisons between, let's say, two different gases, we'll just call them gas one and gas two for right now. We can write the root mean square equation for gas one, right? So it's the square root of 3RT over the molar mass of gas one, and the subscript one there's our first gas. We can do the same thing for gas two as well. We can write the root mean square equation as the square root of 3RT over the molar mass of gas 2. What we can also now do is we can compare these mathematically. And when we compare them, let's say we can compare the root mean square of 1 to 2. We can divide them. We can get a ratio between them. So we can say then the root mean square of 1 divided by the root mean square of gas 2, and we're also going to divide the right sides of these equations. So we have the square root of 3RT over the molar mass of 1 divided by the square root of 3RT divided by the molar mass of gas 2. And if we solve this now mathematically, right, if we rearrange this equation, we can simplify it. We can come up with a relationship that's a little bit easier to interpret. So we can cancel out the like terms that we have, the 3RT. And then when we bring this, divide by the square root of m over 2, we bring this up on top. We end up with the root mean square of gas 1 divided by the root mean square of gas 2 would be equal to now the square root of the molar mass of gas 2 divided by the molar mass of gas 1. So what we actually see now is we can use this equation to compare the values of molecules, compare the root mean square values of molecules with different molar masses. And now that your molar mass could be in any unit as long as they're the same, so that they cancel out. It can be grams per mole, kilograms per mole, any other unit, as long as they're the same when we plug them into this equation. Earlier, we saw that the molar mass had to be in kilograms per mole so that the units would cancel out in the equation that we actually wrote. Okay, so let's take a look at an example. So it says here, determine how much faster a helium atom moves on average than a carbon dioxide molecule at the same temperature. All right, so now we're comparing. Take a look at this. We're going to compare a helium atom, so HE, to carbon dioxide, CO2. Right, and we're looking to see how much faster the helium moves. Okay, and think about it now. The helium has a molar mass, we look it up on the table, of around 4 grams per mole, whereas CO2, carbon dioxide, right, carbon's 12, oxygen is 16, so that's 32 plus 12, that's 44. So molar mass here is about 44 grams per mole, right? So it's a helium obviously being smaller, we would expect it to move faster. How much faster though, right? Again, at the same temperature. This needs to be a fair comparison. So we can use then our equation, the root mean square speed of gas 1, we'll say helium, compared to the speed of CO2 would be equal to the square root of the molar mass now of gas 2, which is CO2, which you said was 44 grams per mole divided by the molar mass of gas 1, which is going to be helium, which is 4 grams per mole. Obviously here, the grams per mole cancel out, so we end up with square root 4 goes into 44, what, 11 times? Just about. All right, so we end up with something like 3.316. So what this tells us then is when we compare the helium to the CO2, this means that the helium moves about this times faster. So about 3.3 times faster than carbon dioxide. Last couple characteristics of gases that we'll take a look at are a direct result of the random motion of our gas particles. Okay, so the random motion of the gas particles results in two more properties called diffusion and effusion. So they sound similar, but they're actually different. So diffusion is simply the mixing of gases. So we have multiple, so more than one different gases as a result of random motion and also frequent collisions between those two gases. So for example, if you take a look at this initial situation here, right? So we have initially, we have two spheres connected to each other by this little stem right in the middle. And originally this stem is closed. So on the left side, we have our purple gas. On the right side, we have our yellow gas. If we open this valve, we allow the random motion of our gas particles to continue, what we would find after the course of time. So let's say after some time, just due to the random motion of gases, some of the purple ones would move into the yellow region, some of the yellow ones would move into the purple region, and so on and so forth. So we have this random mixing now of the gas particles. Okay, and this is what our diffusion is. Okay, effusion, on the other hand, is simply the escape of gas molecules from a hole, from an opening, from a container into a vacuum or a region. So for example, originally, let's say here in this left on the right side diagram, we have our gas in this section, the left section here of our box. Okay, and if we had a hole here that separated, or a region that separated the gas on the left from the vacuum on the right, if we were to open that hole, then these gases would escape through that hole into the vacuum. Okay, that is what we say the gas effuses into that space, right, into that vacuum. And that's again as a direct result of the random motion of your gas particles, whether they're molecules, atoms, whatever. So there's a law, and we're going to see lots of gas laws in the next few sections, called Graham's law of effusion or diffusion, which says that the rate, okay, the rate or the speed, so the rate of diffusion or effusion of a gas is inversely proportional to the square root of its molar mass, right? So whenever we express those proportional relationships, right? We see this little symbol here. That means proportional to. So the rate is proportional to. And we have the inverse, meaning 1 over the square root of the molar mass. Remember this funny looking M, that means the molar mass of whatever that gas is. So again, what this means is, okay, because the molar mass is in the denominator, so as molar mass increases, right? So as the gas particle gets bigger and bigger and bigger, gets more massive, the rate is of diffusion or effusion is going to decrease. And then we'll also see the opposite happening as the molar mass decreases in size or decreases, the gas is smaller, it's lighter, in other words, right? It would diffuse at a much greater rate or speed. Okay, and this is for an inverse relationship, right? And for an inverse relationship, if one thing goes up, the other thing goes down. In a direct relationship, if one thing goes up, the other thing goes up as well. Okay, let's take a look at one more practice problem here, involving the comparisons of root mean square speeds. So it says determine the molar mass and identity of a diatomic gas. So we know right off the bat that this gas has to be something like X being our generic gas and subscript of 2. That means it's diatomic. That moves 4.6 times as fast as CO2. Okay, so now we're comparing two gases. So we can use our equation we talked about previously, where we said that the root mean square of gas 1 divided by the root mean square of gas 2 is simply equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. And we know, we're just told that that ratio or that comparison is that gas 1 moves 4.67 times as fast as gas 2. All right, so we know we can say that our gas 2 here is CO2, and our gas 1 is our unknown. We'll call that X2 for right now. All right, and when we evaluate that, we know that that difference, or that comparison, that ratio is 4.67. Okay, and we know the molar mass of CO2 is 16 times 2 is 32, plus 12 is 44 grams per mole. I'm not paying too much attention to sig figs right now. That's not the point of this. It's just to show you how to solve this problem. So we can substitute our values into this equation, specifically now this side of it, right? So we have 4.67 being equal to the square root of the molar mass. And again, gas 2 here is carbon dioxide, so that's 44 grams per mole divided by the molar mass for gas 1. We don't know what that is. We'll say X grams per mole. All right, so if we have an equation, and this just becomes a math problem now, right? We just need to solve this equation for X. Right, so we evaluate, we solve, and what we'll find then is that the molar mass there ends up being 2.01 grams per mole, and the only diatomic gas that would have that molar mass would be hydrogen, which would be H2. Okay, so if you have equations or relationships or questions like these where, it's not just a simple case of substituting, your M2 and M1 into the equation, but instead now you have to find one of these two, right? Well, then you will need to be given what that ratio is. In this case, it's 4.67.